Okay, so the way we are going to, so we are doing, this is the third day of us doing Lorentz transformation. And I'd like to approach Lorentz transformation a little bit differently today. So, this is what you've seen me do, right? Let me just write it down as a reference. What you've seen me do is for Lorentz transformation, I need some definitions of new variables that's preferred over the old variables for velocity, as in velocity in the unit of speed of light, and this gamma factor that simplifies our formulas a lot. Minus 1/2 or something. And I've written down this transformation multiple times, so let me just quickly write it down without wasting too much time. Ct prime is gamma Ct minus beta x. X prime is gamma x minus beta Ct. And y prime is equal to y. G prime is equal to g. And so far you've seen it as this kind of transformation, some not so simple set of 4 equations, or at least 2 equations. And what I want to illustrate now is what you could call geometry of space-time. So I hope most of you here are familiar with the geometry of geometry, geometry of 2-dimensional space, right? And one of the first things that gets done, sorry, I want a boundary so that I don't intrude on this space. And actually taking this model, I can rewrite this Lorentz transformation the same way. I can represent this Lorentz transformation with a matrix multiplication. Let me do that in this space here. I will, let me just do that. So this becomes, so instead of, so I get a column vector that has 1, 2, 3, 4 entries. Ct prime, x prime, y prime, g prime. And that's a result of multiplying a 4x4 square matrix with another column matrix, which represent the coordinates in the unprimed coordinate system. And now what goes in here is, well, let me try to write it down correctly. So for Ct prime, I want it to be gamma times Ct, so gamma here. And if I expand this out, it's minus gamma beta times x, so minus gamma beta. And then I don't want any y's or g's, so it'll be 0, 0. Okay. For the x prime, so let me go in order. So what I need to get the correct factor for Ct, I need a factor of minus gamma beta. So, all right, minus gamma beta times, I'm sorry, that's that times that gives me that. And then the next entry will give me x. So that's gamma times x, so gamma. And then I don't want y or g, so it's 0 and 0. And the remaining actually becomes pretty simple. To get these 2 equations, you want y prime is equal to 0 times this, 0 times this, 1 times this, and then 0 times g. So it's 0, 0, 1, 0, 0, 0, 0, 1. So once you represent Lorentz transformation in this form, you can see the symmetry you can see kind of features of the transformation so much better. It's represented by a symmetric matrix. Symmetric meaning if you transpose it, you'll get the same thing. All right, whatever that means. I guess I'm not supposed to assume you have taken linear algebra yet. But like you can see, okay, if nothing else, take this away. Imagine the version of Lorentz transformation that's in your textbook, this one. The version that's in your textbook. Just look at it as a matter of convenience. Imagine, let's see, did I skip it? No, more. How far? Okay. So wait, is that right? No. Okay. So imagine. Sorry, you can't quite. This is a bit of a too small, maybe. Wow, it's getting. Sorry. So for those of you who can read, oh, I think I might be able to do this. Yeah. Okay. Show methods. I don't know. Never mind. So this is the set of equations in your textbook, in there as a Lorentz transformation. Imagine memorizing this versus imagine memorizing this matrix. This is a lot easier to memorize. In fact, that's how I have the Lorentz transformation memorized. And what I have memorized on top of this is what the definitions of gamma and beta are. So this is the Lorentz transformation, the way I do like to actually be able to handle it. But to use this feature in full it's a lot works out a lot better if you know linear algebra, and we don't yet. So that's why we are not using this form as often as I would like to.